Hello friends, welcome back to my channel, and it is part 3 of chapter number 7. So in this part we are going to take some reducing agent, hydride transfer reducing agent. Basically we are going to take lithium aluminium hydride and sodium borohydride. We will take how we can synthesize other different reagents using these lithium aluminium hydride and sodium borohydride. So I have also made several videos on these two topics, but in this one I will try to give you only some important points, right, which will be helpful to you during exam. So first we will take lithium aluminium hydride. We all know that this is very strong reducing agent and it can reduce almost all type of functional groups. For example, we have aldehyde, ketones, esters, carboxylic acids, nitriles, lactones. They all are reduced by this lithium aluminium hydride. Aldehyde, ketone, ester and carboxylic acid will directly form alcohol. Nitriles will be converted into amine and lactones will form lactols, right? Then we will take first, very important, that is reduction of amides. Reduction of amide will give you amine. Under normal condition it will give you amine, but if low temperature conditions are given, very low temperature, then it will form aldehyde. So this point is important. If temperature is given in minus 20 to 30 or in minus range, then amides will form aldehyde, right? For example, in this case it will reduce this amide into amine, means we have to simply remove this carbonyl and then we will form amine. So here I am going to take lithium aluminium hydride. Solvent, protonic solvents are not used with lithium aluminium hydride, so ether is used and temperature is 20 degrees centigrade, right? Amine will form. Then next point is isolated double bond and triple bond are not affected by lithium aluminium hydride. They are not affected. But if you have beta aryl alpha beta unsaturated carbonyl, what is the meaning of it? Beta aryl means this is your carbonyl, right? This is alpha carbon, this is beta carbon, and on beta carbon you have phenyl group attached, aryl group attached. So it will be reduced, this double bond will be reduced, and as well as this aldehyde group will be reduced, right? So if you have lithium aluminium hydride and temperature is room temperature or above room temperature 35 degrees centigrade, then this double bond will be reduced, as well as your aldehyde will be reduced to alcohol, right? But if you have low temperature condition, suppose I am using minus 20 degrees centigrade temperature, then only this aldehyde group will be reduced, this double bond will remain unaffected, it will remain unaffected. Or in place of this lithium aluminium hydride at low temperature, you may have sodium borohydride or DiBaL. We will study about these also. Or you can use alane. Alane is formed after the reaction of lithium aluminium hydride with aluminium chloride. We will also study about this alane, right? How we can synthesize them. So in reaction mixture they can give you low temperature condition, DiBaL, sodium borohydride, and a mixture of lithium aluminium hydride and aluminium chloride, right? So you have to understand, under these condition only aldehyde group will be reduced, double bond will remain unaffected, right? So under this condition, this, if you are using beta aryl alpha beta unsaturated carbonyl at room temperature, then your double bond will be reduced. And what about triple bond? When you have this type of triple bond, means at the carbon next to this triple bond you have OH group attached, or you may also have amine attached here. This is called your propagylic alcohol group. So under this condition triple bond will be reduced to double bond, right? You will get this type of product, and especially it will form trans alkene. So in this particular slide we have studied very important points, that we can reduce double bond at higher temperature with lithium aluminium hydride. Under low temperature conditions this double bond will not be reduced, And third point is that lithium aluminum hydride can reduce propagylic triple bond or propagylic alcohols to double bonds, and they will especially form trans alkenes, right? Then we will take certain properties of NaBH4 sodium borohydride. Then we will take some properties which we will study together with lithium aluminum hydride and sodium borohydride. One more important point here which I want to tell you, that in case of sodium borohydride, I have not taken here cerium chloride, or this is not Leuch reduction. Means you have studied previously also that sodium borohydride, we will take this point in later slides, but I want to tell you here only. Suppose you have this type of ketone and I am using sodium borohydride, right? So it can show 1,4 reduction, means double bond will be reduced, as well as this ketone is also reduced to OH, right? And if I am using sodium borohydride with cerium chloride, then only this carbonyl group is reduced, this double bond will remain unaffected. So why I have not taken here this step here, I am not taking cerium chloride in this step, I am only using sodium borohydride, right? And only this carbonyl group, this aldehyde group is reduced, this double bond is unaffected in this reaction. So if you remember that in Claydon-Book summary, I have told you that direct addition is more feasible when you have active carbonyls. For conjugate addition, conjugate addition is shown by less reactive carbonyls. So because this aldehyde is more reactive, aldehyde is more reactive than ketone. That is why this alpha beta unsaturated aldehyde will show direct addition with this NaBH4 instead of conjugate addition. If you have any doubt about this point, I think it will be clear. If it is not clear, then you can watch my video on Claydon-Book summary. This is given in chapter number 22. You can go and watch there, right? It will be more clear. I have taken many more examples there, so you can watch that one also. So let's move ahead. So we will talk about NaBH4. NaBH4 is comparatively less reactive than lithium aluminum hydride. So it can reduce aldehyde, ketones to alcohols, and reduction of esters is very slow, and reduction of amides is not possible with NaBH4, right? So if we want to do selective reduction, then we can use NaBH4. This NaBH4 will only reduce this ketonic group to OH, and this ester group will remain unaffected, right? Suppose I am using lithium aluminum hydride here, then what I have to do, first I have to or you can say that in this reaction I have only reduced this ketonic group, this ester group is unaffected. But suppose I want to reduce this ester and this ketone should remain unaffected, right? We know that ketonic group is more reactive than ester, but we want only ester will be reduced, ketone will remain unaffected, so we have to protect it. And how we can protect it? We can use ethylene glycol under acidic condition, so this ketonic group will be protected, right? It will form this ketal and we have this type of structure. Then we can use lithium aluminum hydride, it can easily reduce esters to alcohol. Then we can use acid, so it can remove this protecting group and we have ketone back in the molecule. This is what I have told you, that if I am using sodium borohydride in presence of methanol, then this double bond will also be reduced, means it will show 1,4 addition. And suppose I am using NaBH4 in presence of cerium chloride, then it will show direct addition, means this double bond will remain unaffected. So this example is very common, but certain important things about this reagent, that is sodium borohydride with cerium chloride. Suppose in this reaction we have two groups here, this aldehyde and this alpha beta unsaturated ketone. So this sodium borohydride in cerium chloride will attack on less reactive group. And out of these two, which one is less reactive? This alpha beta unsaturated ketone. Aldehyde is more reactive than ketone, so it will remain unaffected. And because with cerium chloride, this will show direct addition, so only this ketonic group will be reduced, right? And suppose I have aldehyde and ketone both present in a molecule, then you can easily recognize that this ketone is less reactive than aldehyde, so this ketone will be reduced, this aldehyde will remain unaffected, right? And then question come, what will be the attachment side of this OH, what will be the plane of its attachment? So I have told you in case of Claydon book summary, where in the chapter on cyclic molecules, I have told you that incoming group tries to attack from the side which is less hindered. In case of 4 and 5 membered rings, that incoming group try to attach from the side which is less hindered, right? So because we have here this group attached above the plane, so hydride, this sodium borohydride basically provides us H minus. So this hydride will attack from the less hindered side, that is from the below the plane side. And when it will attack from the below the plane side, this OH will come above the plane, right? So this will be the side of attachment of OH. So why this happens, that in presence of the cerium chloride, only less reactive carbonyl group is reacting. It is considered that cerium, this cerium Ce plus 3 will form complex with more reactive carbonyl, and when it will form a complex, then it will not participate in reduction, only the less reactive one will participate, right? Then if I have told you that esters react very slowly with sodium borohydride, and suppose in a molecule you have ester plus amide group together, and suppose you are using sodium borohydride, and with this sodium borohydride suppose I have calcium chloride, then this ester will be reduced, this will be reduced to alcohols, and this amide will remain unaffected. In place of this calcium chloride, you may also have titanium chloride or Lewis acid. Any other Lewis acid can also be used with it, but these conditions should be there, otherwise this reaction will be very slow, right? So don't be confused when you have ester and amide together with NaBH4 and with any of these Lewis acids and calcium chloride, then ester can react, right? Sometimes we think that ester cannot be reduced by NaBH4, but under certain condition it can react. So it is an important point. So we have seen examples where this your less reactive carbonyl is reduced by sodium borohydride. We have seen this in presence of NaBH4 and cerium chloride, less reactive carbonyls can be reduced. But suppose if I want that aldehyde should be reduced but ketone should remain unaffected. Suppose I have both aldehyde and ketone present in a molecule, and I want only aldehyde should be reduced, ketone should remain unaffected. So I can use tetra N-butyl ammonium triacetoxy boron hydride. I can use this one. If I will use it, then aldehyde will be reduced, right? What is its name? Tetra N-butyl ammonium triacetoxy boron hydride, right? This reagent can be present in this form, or we can have its derivative supported on a solid structure, solid sorbent like this one, right? So here I have chloride group, nitro and ketonic group present, right? So only this ketonic group will be reduced. Most of the time this sodium borohydride doesn't affect halides and nitro compounds, but if I am using this one, then it is sure that it will only affect this ketonic group. And what is about the side of attachment of this OH? Because this group is below the plane, right? So incoming group, that is hydride, will attack from the side which is less hindered, means it will come above the plane and OH will go below the plane. This concept will be more clear if you consider this 6-membered ring in chair form, right? So suppose I am using here lithium aluminum hydride. This lithium aluminum hydride or sodium borohydride will provide us hydride, right? So most of the time in case of cyclohexane derivatives, we have also discussed this point previously, that in case of cyclohexane derivatives, this hydrides always or any oncoming nucleophile tries to attach from the side axial. It always tries to attack from the axial side, and when it will attack axially, then this OH will go equatorial, right? So we have this product as well as we can have this one, axial alcohol also, but the major product in which H attached axially. But suppose I have here methyl group present axially on this carbon, right? At third position I have methyl group attached, then it can show diaxial interaction. That is why with this lithium aluminum hydride, hydride will attack equatorially, and the major product will be in which OH is axially. This will be your major product. Or if I am suppose using L-selectride or any other bulkier lithium aluminum hydride derivatives, means suppose I am replacing this H with a bulkier group, then it will become a bulkier derivative, or you can say it will become less reactive and more selective in nature, as well as it is bulkier in size. So in that case also this hydride will attack from the equatorial side. Instead of this axial side, it will attack equatorially because of the bulky nature of this L-selectride. So the ratio of major to minor will be increased by using this L-selectride. Suppose I have major product this one, and in minor amount I have also OH equatorially present, and in case of lithium aluminum hydride, this ratio is 55:45, but if you are using L-selectride, then this ratio will become greater than 99% and 1%, right? So you can use this one. So this is the case when I am using hydride derivatives. So always remember that whenever I have this hydride derivative, then hydride H minus will tries to attach from the axial side, unless we have methyl group present at axial position. But suppose you are using lithium or sodium in ammonia, means if you are using this dissolved metal as a reducing agent, we have discussed about these dissolved metal in previous chapters, that they preferentially forms thermodynamically stable products, means your OH should go in equatorial direction. We have discussed about this point previously also. I will tell you this in brief here, that suppose I have this is cyclohexanone, right? So bond will break like this. So when bond breaks, what you will get one radical here and O minus here. So we have discussed this point in previous chapter, that O minus will go in equatorial direction. This will be a thermodynamically stable product. If O minus go in equatorial direction, means OH will be in the thermodynamic in equatorial position exclusively. This will be our major product. Whatever the type of initial reactant we are using, whether we have methyl present here or not, always it will give us thermodynamically stable product, means OH will go in equatorial direction, right? So this is very important point. Then next is if I am using epoxides. So suppose I am using lithium aluminum hydride only, there is no acid used in this reaction. So with lithium aluminum hydride, this oxygen is not activated in nature now, because we are not using any acid here. So it will attack on less hindered carbon. It will attack on less hindered carbon with inversion in configuration, right? So when it will attack on it, we will get this type of product. But if I am using sodium cyanoborohydride, we will study about this sodium cyanoborohydride a little bit later, and with it I am using a Lewis acid, right, this one, then what will happen, this oxygen will become activated, right, and with activated oxygen it will form, this hydride will attack in such a way that it will form a stable carbocation. If you remember, in Claydon-Book summary, we have studied opening of epoxide ring by two mechanisms. One in which this oxygen is not activated and nucleophile attacks on less hindered carbon with inversion configuration, right? And second one in which this oxygen is activated and nucleophile attacks in such a way that formation of more stable carbocation take place. Right, first thing, this ring will open, then more stable carbocation will form at this carbon, and then nucleophile will attack on it with inversion in configuration. So suppose previously this oxygen is above the plane, and after inversion means we have to form more stable carbocation. More stable carbocation means we will have a structure like this, right, and with inversion in configuration means in starting this methyl was below the plane, so after reaction it will come above the plane and H will go below the plane. This O minus will take a proton and it will form OH, right. So this is very important. If you have any doubt about this epoxide ring opening, then you can watch Claydon-Book summary about this epoxide ring opening, because this is very important point, how the epoxides open in presence of acid and in absence of acids, right. This point is very important. Then we have taken many properties of lithium aluminum hydride, that it can reduce almost all type of functional groups, right. One more important thing about them is they can reduce primary and secondary halides to alkenes. Reduction of tertiary halide is very slow, and they will form alkenes, right. And if you are using aryl halides, then they will form corresponding hydrocarbons, right. In addition to that, if you have sulfonate esters, they will also form, they will be removed and hydrocarbon will form, right. For example, in this case I am first using this tosyl chloride in presence of pyridine. So we all know how it will react. It will attack on less hindered OH group. We have here primary and secondary OH, so it will preferentially attack on this primary OH. So it will form tosylate group here, right. Then we will use lithium aluminum hydride, and this lithium aluminum hydride will remove this group. This whole group will be removed, and only we have here, so it is preferentially attacking on this sulfonate ester without affecting these all functional groups. It is preferentially attacks on this sulfonate esters. So there are lot of reactions left in this chapter, and I think I should cover next, I will upload next part tomorrow, because it will be more confusing if you take many more reactions simultaneously. So please try to understand all these points very clearly. These are very simple, but certain points are tricky, right. So first revise them. I will upload next part of it tomorrow only, right. You don't have to wait so much. I have created second part, but I will upload it tomorrow, right. So you can study that one separately. So good luck for your examination, and please do revisions, which is very important. Thank you so much for watching, and if you like my videos, please share my videos with your friends.